The topic is magnetostatic fields or the steady magnetic field. The steady magnetic field is produced in two ways. First, the steady magnetic field can be produced when the charge is moving with constant velocity. The charge with constant velocity is called direct current. Means when a current carrying conductor where the current is flowing with constant velocity, then there is a production of magnetic field. Here the magnetic field is called static magnetic field because the magnetic field is due to the constant current, that is DC current. So it is called static magnetic field. So this is the first way for the production of magnetic field, that is steady magnetic field, that is by using a direct current in a current carrying wires. And there is a second way for the production of steady magnetic field, that is by using a permanent magnets. So these are the two ways for the production of steady magnetic field. First is by using direct current and second by using permanent magnets. Okay. Now there are two laws which governs the steady magnetic field. The first is called BIOT-SAVART's law and second is Ampere's circuit law. BIOT-SAVART's law is a general law that is applicable for any current distribution, while the Ampere circuit law is applicable only for symmetrical current distribution. We note one point here. In case of magnetostatic field, we consider a current distribution, as in electrostatic we consider a charge distribution. So this is a point here because the magnetic field is produced due to the constant current, DC current. So here we consider a current distribution. So the BIOT-SAVART's law is a general law applicable for any current distribution, while the Ampere circuit law is applicable only for symmetrical current distribution. So as we compare magnetostatic with electrostatic, BIOT-SAVART's law is similar to Coulomb's law, while the Ampere circuit law is similar to Gauss's law. So these are the two laws which governs the steady magnetic field. First is BIOT-SAVART's law and second is Ampere's circuit law. And there is a difference between these two laws. Now, there are many applications where the magnetostatic fields are used. Here some of them are. First is magnetostatic fields are used for the development of motors, for the manufacture of microphones, telephone ringers, transformers, used for high speed velocity device, in particle accelerator like cyclotrons, in electromagnetic pumps and so on. So there are variety of applications in which magnetostatic field are used. Now we again note one point. As we compare magnetostatic with electrostatic, in case of electrostatic, the electric field intensity is represented by capital E vector, while the electric flux density is represented by capital D vector. Similarly, in magnetostatics, the magnetic field intensity is denoted by capital H vector, while the magnetic flux density is denoted by capital B vector. So this is a difference, and we know that the electric flux density have a unit, that is Coulomb per meter square. Similarly, the magnetic flux density B vector having a unit Weber per meter square. So we have to care about it. The magnetic field intensity is denoted by H vector, while the magnetic flux density is denoted by capital B vector. So as we know that the steady magnetic fields are governed by two laws. One is BIOT law and second is Ampere's circuit law. So we talk about the first law. The first law is called BIOT-Savart's law. So to explain this, we consider a wire which carries a current I. Means through this wire a steady current, DC current I is flowing. Now as we know that in case of steady current flowing, there must be an production of magnetic field. So here the magnetic field is represented by its intensity, that is called magnetic field intensity, capital H vector. Now what is the direction of this magnetic field? The direction of this magnetic field intensity is determined by using right hand rule. Here we have to determine the direction. So we use a right hand rule. So according to right hand rule, the thumb direction represents the direction of flow of direct current, and the curved finger represents the direction of magnetic field intensity. So to the left hand side, we see that the finger come out. So the magnetic field intensity is outward to this page, while to the right hand side the magnetic field intensity is input to this page. So this is a way to determine the direction of magnetic field intensity by using right hand rule. So this rule is applied here in case of BIOT-Savart's law, and this rule is applied in all the way in magnetostatics. So this is a conventional representation of electric field intensity H, or it is also used for current also. So as we know that the arrowhead, when we see a top view of arrow, we see a point here. So the point represents the outward direction, and cross is a tail of the arrow. So cross means in of the page. So this is a conventional representation. So for BIOT-Savart's law, we consider a wire which carries a constant DC current I. So by using a right hand rule, so we give a direction of magnetic field intensity H. So this wire carrying current I, and to the left side of this wire the magnetic field intensity is outward, and to the right hand side of this wire the magnetic field intensity is inward. Okay. Now for the BIOT-Savart's law, we consider a small length, that is called differential length. Now since there is a current I flowing through this element, so here we consider a differential current element. This differential current element is denoted by I into dl. This is a small differential current element, that is I into dl. So, and we have to determine a magnetic field intensity at point P. Suppose we take a point P, and at this point we have to determine the magnetic field intensity H. So we consider point P to the right side. So from a right hand rule, at point P the magnetic field intensity is inward. Now the current element IDL to the point P having distance capital R. So there is a unit vector R from current element Idl towards point P. Now, according to BIOT-Savart's law, the differential magnetic field intensity, that is dH, produced at a point P by the differential current element Idl is proportional to the product Idl and sine of the angle between element and line joining point P to the element, and is inversely proportional to square of the distance R between point P and element Idl. So this is a statement of BIOT-Savart's law. So from figure, since the magnetic field intensity is due to a small current element Idl, so here we talk about a differential magnetic field intensity denoted by dH. Here first we represent in magnitude form. So in magnitude form the current element is Idl, and in case of differential magnetic field intensity it is represented by dH. So dH is directly proportional to product of Idl and sine of the angle alpha, that is between element Idl and distance R towards P. So this is angle alpha, and inversely proportional to square of the distance. Okay, now there is a constant of proportionality which is given by K, and in SI unit the value of K is 1 upon 4 pi. So accordingly the magnitude dH, that is magnetic field intensity dH, is equals to I into dl sine alpha upon 4 pi R square. So this is according to BIOT-Savart's law, and with the help of this law we can determine the differential magnetic field intensity dH. So this is in magnetic form. Now if we talk about in vector form, so we use a current element, differential current element Idl in vector form, that is I into dl vector, and the distance between element and point is R having unit vector AR. So since you know that in cross product we get a sine term, so we use a cross product of current element Idl vector into unit vector R. So by using this we get a sine alpha. So in vector form the dH vector equals to Idl vector cross AR vector, AR is unit vector, upon 4 pi R square. Now as we know that the unit vector R is equals to vector upon its magnitude. So by using this formula, so we get dH vector equals to Idl cross vector R upon 4 pi R cube. So this is a BIOT-Savart's law, and this we use a right hand rule to determine the direction of magnetic field intensity capital H. Now the next is the current distribution in magnetostatics. So in magnetostatics the current distribution are basically of three types. First is line current, second is surface current, and third is volume current. The surface current is denoted by current element I into dl vector. The surface current element is denoted by K vector into ds. Here K vector is called surface current density. Volume current is denoted by vector J into dV. So these are the three current distribution in magnetostatics. So we talk about one by one. First is line current. The line current distribution is represented by I into dl. So here we consider a line or wire which carries a constant current I. So here we take a small element and it is given by I into dl vector. So this small element is called line current. Similarly, in case of surface current, the steady current I is flowing on the surface of any conductor. Now, according to this surface current distribution, there is a surface current density K vector. In magnitude form, the surface current density K is equals to I upon B. I is the current flowing through the surface and B. What is B? B is a perpendicular distance to the direction of current. So this is a simple, the surface current density K equals to current upon perpendicular distance to the direction of current flow. So in case of surface current distribution, we use element K vector into ds, where K is called surface current density. Third is volume current. Volume current is denoted by vector J into dV. Here we consider a volume. Now here we consider a cylinder. In this, a constant current I is flowing. So here we consider a volume current density that is denoted by vector J. And here the volume current distribution is vector J into dV. So these are the three current distribution in magnetostatics: line current I into dl vector, surface current K vector into ds, and volume current, that is J vector into dV. So here we note one point: surface current density. Surface current density is denoted by K for current flowing on the surface of a conductor and is defined for uniform current density. Uniform current density means the current is uniform, flow with constant velocity. So from here we can determine current with the help of surface current density in terms of surface current density K. So I equals to K into B. Now if for non-uniform surface current density, we use an integration. Here the current I is equals to integration surface current density K into dN, where dN is a differential element of path across which current is flowing. So when there is a non-uniform surface current density, we use an integration to determine the current I. So this is about surface current density K, that is noted by K. So the current distribution or current element in magnetostatics can be expressed in terms of line current, that is Idl Kds and J into dV. So in place of Idl vector, we can write K vector into ds, or we can also write J vector into dV. So accordingly, the BIOT law has three forms. First is in case of line current distribution, second is for surface current distribution, and third is for volume current distribution. So for line current distribution, the formula is line integral I dl vector into unit vector r upon 4 pi r square. So in place of unit vector r, we can write vector upon its magnitude. So this is a form. In case of surface current, we use a surface integration, that is vector k ds into cross unit vector r upon 4 pi r square. Similarly, the volume current distribution, the magnetic field intensity H vector is equals to volume integral J vector dV cross unit vector r upon 4 pi r square. So With the help of Boyles law, when different current distribution is given, we can determine the magnetic field intensity H in magnetostatics by using right hand rule.